Hello, students. Welcome back to Vassiver. So, we're going to be continuing talking about derivatives, and today we're going to talk derivative as a function. So, recall last time we learned the definition of the derivative as the limit, and specifically as the following limit. So, f prime, right, of a is equal to limit as h approaches 0 of f of a plus h minus f of a divided by h. And our main goal, right, our main goal is to get rid of h in denominator and find the equation at the point a. But now, today, we're going to be essentially talking about removing that point a and just talking about the general formula for the f prime of x, right? Because f prime of x is going to be a function as well, right? It's going to be the derivative function, so the slope function of the main function f of x, right? And we're going to describe the rates of change, so the slopes at each of the point of the main function. All right, so remember, we did last time some of the equations, some of the examples. We found some of the slopes. So today we're going to talk about some interesting things, right? We're going to recall from algebra how we were learning about zero slopes, right? So here, for example, we're given a curve, right? This curve has some peaks, right? Some peaks troughs here. So we know that at some points, we actually might have a zero slope, right? A zero slope. So that turns out if we find, so if that's the slope, right? If this is the slope of a function, or, to be more specific, right? If we are given a function, right? This peaks are gonna be the zeros of the velocity function, right? Which is not velocity, the slope functions. So this is our function f of x, right? This points at which the slope is equal to 0, right? Where we have a perfectly parallel line to the x-axis. That these points are going to be the zeros of the f prime of x function. This is going to be the zero. So this is very, very important, right? It gives us some interesting properties of the derivative. So what does that mean? Well, we can actually find the maximums and the minimums at the points, right? The maximums and the minimums, because, well, this is essentially, this point is the minimum point, right? So we know that if we find a derivative, right, we find the slope of this function and find one of the zeros of the velocity, that will give us the minimum, right? The minimum number right here. So, okay. Now, what we want to do is, well, let's find a derivative of some functions, right? Last time we did it for, polynomials, we did x squared. So now let's go ahead and do something more interesting. So our first example, right, will be example 1, specifically for f of x is equal to square root of x. Right, this is interesting. This is unusual. So, well, let's go ahead and get to it. So f prime of x is going to be a limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, so if we plug in, we're going to have limit as h approaches 0 of square root of x plus h, right? So it has to be under square root. So this will cause us some difficulties, which we will have to resolve, remembering the algebra rule, and then divided by h. So in order for us to do that, we have to rationalize the numerator. So in algebra 1, the rationalization is basically we have to take a conjugate of this expression, and the conjugate meaning that we will have to change the sign to plus. So if we go ahead and multiply by square root of x plus h plus square root of x, and we also divide it, right? This is a unit multiplication because we don't really change anything, but we want algebraically simplify it. So x plus h plus square root of x, right? So, okay, so what are we going to have here? So a numerator, right, limit as h approaches 0. So if we do simplification, we will end up having x plus h minus x, right? This is a difference of squares, essentially. But now we just don't have squares, we have the square roots, which cancel out. And denominator will be just h times square root of x plus h plus square root of x. Okay, so here, if we open up the parentheses, we're just going to have limit of h approaches 0 of h divided by h times square root of x plus h plus square root of x. Perfect. So notice, again, our main goal has been reached. H and h cancels out. So that means we're just going to have the limit as h approaches 0 of 1 over square root of x plus h plus square root of x. So if we evaluate this limit, we're just going to have 1 over square root of x plus square root of x, which is equal to 1 over 2 square root of x. Perfect. So we found out that f prime of x is going to be, so for this equation, is going to be 1 over 2 square root of x. Right. For your own example, for your own practice, you can try to find the derivatives of 1 over x squared. Or so you can practice this. Find 1 over x. So f prime of x of the following: 1 over x, then x cubed, then x to the fourth, then you can try to find the e to the x. Right, this one's going to be interesting. Okay, we will be covering it, but later. Right now, you can try to think about it, and maybe that will help you out to work with derivatives even better. So now, as we going through, right, and I can put your answers here underneath. So this one's going to be negative 1 over x squared. This one's going to be 3x squared, 4x cubed. This is going to be e to the x. So this is the answers, okay, of f prime of x, actually. So okay. Now, let's discuss some other notations. So throughout the history, there have been a lot of people coming up with the notations, right? There's been the notations of Newton, of Leibniz, of Lagrange, and Euler, right? And all of them had essentially different notations of derivatives, but they had the overall same vision, right? Same vision of the derivatives. So we essentially, our favorite is the Leibniz, right? So even though some of the notations we still use, right, like Newton's notation and the Leibniz notations are the most common ones, but sometimes depending on application, you might see the other notation as well, right? So for example, right, we can have f prime of x, which is the same thing as y prime, right? So Newton liked to write either y prime or, sometimes you can see y dot, right? This is also. Then it's the same thing as dy over dx, which is rate of change, right? But d is instantaneous change, which is the same thing as df over dx, right? This is Leibniz. Leibniz loved that notation, right? And sometimes you can also see mathematicians like it as d over dx. So we treat this as the operator. This is an operator on f of x, right? Derivative is an operator. It's an operation, right? Mathematically, it's like addition and subtraction, right? We treat it as an operation. So that's what's actually happening, right? We're treating as an operation. We're performing an operation onto the function. Okay, and of course, Euler's notation would be dfx, or also sometimes you emphasizing that dx of f of x, right? You're using x variable here. That's what it means. So, oftentimes, so for all of those notations can be seen in mathematics, from mathematics. So this kind of notation can be seen in aerospace engineering and mechanical engineering, so specifically fluid dynamics. This is one very common, right? Because every field wants to be special and every field wants to be different. So essentially they choose themselves the different stuff. So this is the rest of them are math plus physics and plus chemistry and any other possible sciences. All right, so let's again write the essentially more of a definition here. So and of course, if we want to evaluate a derivative, right? If we want to evaluate, so there's many ways we can write. Of course, we can write. So how do we evaluate, like, for example, here at this one, right? Because for this one, we can say, well, f prime of a. How do we do this one? This one's going to be dy dx at x equal to, right? So the notation is just a different way of writing it. So this is what it means. It means evaluate it at x equal to a, right? Which is, so you can see that sometimes in papers and sometimes in writing, we would try our best to avoid, we need more space. We don't need to take more space. We need to have the least amount of space, right? We want to take the least amount of space and give the most information possible, right? And especially right in higher mathematics, that's when it's crucial. Right here, we can use different ones and we can be okay. But here, in previous times, we would run out of paper. here, since we're digital, we're not going to run out of paper, right? We might run out of memory, but not going to run out of, because if we get more memory, we're going to be okay. But for papers, it was much more difficult. So now the definition. So a function f is differentiable, right? So essentially f, we can take a derivative of f at point A if, of course, f prime of A exists, and specifically that limit exists, and it is differentiable on the open interval if it is differentiable at every number at the interval, right? So this one is very important, differentiability, because it comes with a continuity. Right, and remember, we did cover the continuity, what it means to be continuous for a function. That means we can evaluate the limit of the function and the function value trying to match each other, right? This is the most important part, which they give us the proper answer. So here we have, for example, right? Let's take a look at example here. So example, we want to find out f of x equal to absolute value of x, right? Is it differentiable? And we are asking like a general question, right? So we know that essentially we will have two limits to take a look at. Why? Because absolute value of x has two possibilities. It's either x for x to be greater or 0, or it's negative x for x to be less than 0. So this is a kind of piecewise function, right? So that means we can say, okay, well, f prime of x, so we're going to consider it for x being greater than 0, greater or equal. So we're going to have limit of h approaches 0 of x plus h minus absolute value of x over h. So that's going to be limit of h approaches 0 of x plus h minus x over h. So that's going to be equal to 1. Okay, the slope is going to be equal. How about the other side? So f prime of x, so from the other side, right? So x greater or equal to 0, or just greater than 0 in this case. And here x is less than 0. So we will have that limit of h approaches 0 of, so again, absolute value of x plus h minus absolute value of x over h is going to be a limit of h approaches 0 of negative x plus minus negative x over h, which will give us negative 1. Okay, so we know that it's differentiable. So, okay, we know that it's differentiable for x greater than 1 or x, less than 1, but how about x equal to 0? So for x equal to 0, let's find out. F prime at 0 is going to be equal to, so limit as h approaches 0 of absolute value of 0 plus h minus 0 absolute value over h. So that's equal to limit of h approaches 0 of absolute value of h over h. Right, so this is actually very similar to what we have for the right hand and left hand limit. So let's find the right hand limit. So limit as h approaches 0 from the right. Right, and when we're approaching from the right, it's actually going to be positive, right? We know that in the previous, when we're approaching from the right, x is greater than 0. This is going to be h over h, which is equal to 1. When we're approaching from the left, we know that we were negative, right? Less than 0, so it's going to be negative h, which is equal to negative, So let me actually make h over h is equal to negative h over h, which is equal to negative 1. And these two limits, limit of h approaches 0 plus, is not equal to the limit of h approaching left. So what does that mean? That means that f prime at 0 does not exist. So that means that means that y, so f of x is equal to absolute value of x, is not differentiable at 0, at x equals. Okay. So that leads us, right? We saw that the limit is violates. So that means the function is what? Not continuous, right? This means that it's not continuous. So let's form a theorem. And that's going to be a theorem of differentiability. So in opposite. So if f is differentiable at a, then f is continuous at a. Okay. So we know, right? We know. So let's go ahead and do proof here. So we know that we want to find f prime at a, right, which is going to be a limit as x approaches a of f of x minus f of a over x minus a, right? So we know that what we want to find, right, what we want to find is essentially we have to rewrite some things. So let's rewrite it the following way. So we're going to take a look at f of x minus f of a, right, which is the same thing, right? Assuming we are assuming that, you know, x is not equal to a, right? That's why we're taking a limit. So that means we can write it as f of x minus f of a over x minus a times x minus a, right? Okay, that's perfectly valid. That's fine, right? Because this is the same things. But now let's take a look and take a limit, right? We're going to take a limit from both sides, okay? Limit as x approaches a, right? So what are we going to have? We will have limit as x approaches a of f of x minus f of a, right, is equal to limit of x approaches a of f of x minus f of a over x minus a times x minus a. So remember the product rule law for the limits. So we're going to have that limit of x approaches a of f of x minus f of a, right, is going to be limit of x approaches a, right, of f of x minus f of a over x minus a times limit of x approaches a of x minus a. So what is this? So what is this right here? This is f prime of a. What's this going to be equal to? That's going to be equal to 0, right? So that means we're going to have what? We're going to have f prime of a times 0, which is equal, 0. Right, actually, put it here, 0. Okay, so we just showed, right? We essentially just showed that the limit, right? So what do we showed here? Showed that, you know, the limit of x approaches a of f of x minus f of a is equal to 0. Okay, perfect. So the way we can work it through, right? The way we can through is we now and use the distribution line, right? We can distribute the limits. So we're going to have limit of x approaches a of f of x minus limit of x approaches a of f of a is equal to 0. So what is this limit? This limit, I mean, we don't actually compute anything. This is just f of a by the rules, right? By the rules of limits. So that means we're going to get that limit of x approaches a of f of x is equal to f of a, which is exactly continuity. This is exactly meaning that it's continuous, right? It means that it's continuous by definition, right? That's exactly what we wanted to show. Perfect. So that would be the end of this proof. All right, awesome. So now we know that if it's differentiable, it's going to be continuous. So okay, perfect. Now, a few more notations, right, which we should mention. So remember, last time we talked about the position, velocity, and acceleration. So, well, acceleration is derivative of the velocity, right? But sometimes, you know, we want to have multiple derivatives. So what if we want to take multiple derivatives, right? Then there is multiple ways. So if we have f prime of x and we're taking a derivative prime, we can write it as f double prime, right? And the same thing if we have dy dx, right, and we want to take a derivative, so d dx, that's going to be d2y over dx squared. Right, this is going to be the second derivative, right? We're going to call it second derivative. And essentially, we can do as many as we want, right? Nothing stops us. But for f double prime, right, if we go higher, oftentimes in the literature, it's either going to go into Roman numerals, right? Because like if you have 4, 5, 6 derivatives, it's already kind of complicated to draw 6 lines. So it's easier to go into Roman numerals to not confuse with the powers, right? Because sometimes we want to have a function in the power, so we have to be very cautious about the notations that we use. So, and of course, as I said, right, last time we did velocity and position. So this is going to be just a reminder, right? So velocity is equal to position derivative, or ds over dt, right? Same thing. Acceleration is going to be equal to velocity derivative, or the double derivative of the position. And of course, if we want to do the third derivative, right, which we usually, there is some instances that we might use it in physical sense, right? But that's what it is, right? And in science, the triple derivative is the change of the acceleration, and that term in physics called the jerk. The jerk is the rate of change of acceleration, and the large jerk means a sudden change, right, in acceleration, which causes a very abrupt motion in the vehicle or wherever you are moving in. So it happens, right? It happens, and this is one of the physical applications. But it's you'll rarely see that. And of course, if you want to find an arbitrary nth derivative, that's going to be one of the common notations to see, right? Parentheses are important to not confuse it with powers, because what if you want to do f squared, right, instead of the powers? So, okay, and of course, you guys can think about an example for you to work on. So if you have f of x, right, is equal to x cubed minus x, so find f triple prime of x, and let's find f quadruple prime. So it's going to be I prefer using Roman numerals, so of x, or right, so fourth derivative, right? And it turns out, right, the answer is going to be 6, and here the answer is going to be 0. All right, perfect. So next lesson, we are going to talk about some of the simple rules of differentiation. So, because we don't have to always evaluate those kind of limits. And next time we're going to dive into the differentiation. Right, thank you, students, and I'll see you all next time.